Welcome back to physics. This week we're going to ponder electric circuits. So kind of picking up where we left off last week with electrostatics. The one concept that we're going to pull strongly over besides basic use of charges is the idea of electric potential or voltage. So recall that means joules per coulomb, energy per charge, or work done per charge. But now we're going to analyze that in a dynamic situation, which means we're no longer in situations where our charges more or less are at rest, but now our charges are moving and there is somewhat of an organized or a net movement in a certain direction, which we're going to develop into the idea of an electric current today. Leading up to electric current, I wanted to take a minute to talk about batteries since we did some demonstrations the other day with batteries. Your basic idea of a battery, you start with chemical potential energy. You have two chemicals essentially in the battery, your two reactants. One of those reactants is this central rod, and I'm going to highlight that. That's one of the reactants. And then your second reactant is the cup that goes around the sides here. So all along the outer edge and the base and all around, that's your second reactant. And the basic idea, you have chemicals that react. Well, some chemicals that react will produce heat. Some will produce light. There are different end products. Well, the end product of the chemical reaction that takes place inside of a battery is that charges are transferred. One of the substances takes on electrons, the other one loses electrons. Now, if you just mix those chemicals together, you'll just get an exchange of charges. If you separate those two substances by this electrolyte solution in between, that's a conductive substance which will allow the chemical reaction to take place, but it takes place at a distance so that you get those charges flowing, you get an electric current. So then when we hook this battery up into a circuit, this chemical reaction takes place, and the two different terminals, the top up here, positive. It does not indicate that it is a positive charge. Rather, that indicates that it is a higher level of voltage or electric potential. So if we have 1.5 volts battery, this will be a plus 1.5 volt or 1.5 joules of work have been done on each coulomb of charge that has been placed on that central rod. The cup then would be at 0 volts. So you have a different amount of energy, different amount of work that has been done. When you connect these in a circuit, so I'm going to draw a circuit here. I'm going to put the symbol for a light bulb out there. When you connect this in a circuit, then your charges are going to flow. And we're going to talk in much more detail about that in just a second. Your charges flow. That means the chemical reaction starts to occur. And you react that central rod with that outer cup. Well, eventually your battery dies. And what happens when your battery dies is that you have completed the chemical reaction for those two substances, which basically means that central rod is dissolved away. It's not there anymore, okay, because it has reacted, it has combined, it's no longer there. So then the concept, the term of recharging a battery is very misleading. When a battery is dead, it has not run out of charge. It has completed the chemical reaction. When you recharge a battery, you do not fill it back up with charge. Rather, you apply a backwards electric potential across it to be able to reverse the chemical reaction and separate the chemicals back out. Physically, then, what you're doing is you are rebuilding or replating that central rod that had dissolved in the process of the chemical reaction. Some chemical reactions in batteries are reversible, some are not. That's why some batteries can be recharged and others cannot. Now, each time you recharge it, and you rebuild, you replate that central rod, it doesn't always build nice and neat like it did when you first had it. it somewhat forms a little bit more randomly. So I'm going to use a different color this time, so hopefully it's a little more visible. So then when I recharge this central rod may look something more like that, where it's a little bit more random in shape. And as I recharge it and recharge it and recharge it many, many times, sometimes it becomes more random. If it ever happens to rebuild and have part of it that extends out all the way out here to the outer cup, then there's a connection, and then that battery is dead. So that's the basic idea of a rechargeable battery. This is a simple geometry here that I've shown. Other batteries that are flat or discs or different shapes, it's the same basic concept, but it's a different geometry to that same process. Let's talk about an electric current. Here we have a light bulb and a stopwatch. And what I'm going to do is start the stopwatch at the same instant that I plug in the light bulb. And I want you to tell me to stop the stopwatch when the electrons from the outlet have reached the light bulb. We're assuming this is a direct current application. So I stopped at a time of a little over 1 second. I'm going to clear that and start again. Now I haven't stopped the stopwatch because none of the electrons from the outlet have reached the light bulb yet. So let's ponder what's going on with electric current. An electric current is basically a flow of charges, but specifically it is a rate. The rate of flow of charges past a certain point in a wire. So being a rate, that's a ratio of the quantity of charge to the time period. Let's pause for a second to check our light bulb and our timer. We're at about 40 seconds, and still not a single electron has made it from the outlet to the filament of that light bulb. So then in symbols, current is symbolized with an I, charge is a Q. This is a change in charge, delta Q, over time, delta T. So then your equation to be able to calculate electric current, I is equal to delta Q over delta T. In units, you have charge in coulombs, you have time in seconds, and a coulomb per second is an amp or an ampere. The symbol is just the capital letter A. So if you have a current of 1 amp, you have 1 coulomb of charge flowing past a point in a wire each second. We have previously said that a coulomb of charge is a lot of charge. Well, an amp of current is a pretty ordinary amount of current. Typical incandescent light bulb, maybe 100 watt, you have about 1 amp of current flowing through that, or 1 coulomb per second. So now let's talk a little bit deeper about exactly what is going on with an electric current. Looks like we're at about 2 minutes and 10 seconds. Still not a single electron has made it from the outlet to the filament of that light bulb yet. So now let's picture what exactly is going on in that electric current. We have our electron here. It needs a reason to flow. So in order to run something, just like we did for our light bulb, we had to plug it in or we have to connect it to a battery. And the purpose of that battery is to supply a potential difference or a voltage across the wire. We'll say this end is our high potential, this end is our low potential. What happens then is that charge is going to be made to flow. Well, when it starts to flow, there's a problem. You have your solid wire that's shown here with all the atoms in it, and they're in the way. And so as our electron starts to move, it runs into an atom. When it runs into an atom, it's going to bounce off that atom and hit another and bounce. And as you can see, our electron goes through the wire, but it's not going very fast. It's not progressing forward very fast. It's not moving in a very direct route because it's running into so many things that are in the way. And so on our light bulb, it takes those charges a very long period of time to be able to move through that wire. So on our light bulb and timer, we are at just under 4 minutes, and still not a single electron from the outlet has made it to the filament of the light bulb. If we kind of arbitrarily drew that path, and I don't remember exactly the path that I took, so I'm going to draw kind of just a random bouncing path, but our electron travels and it bounces from atom to atom to atom in a very indirect path, running into lots of things in the process and not getting anywhere very fast. There are two different velocities we can talk about. The actual speed of that electron on one of those given yellow arrows. Your electrons are moving in the neighborhood of about 1 million meters per second. So if I highlight one of these individual paths, that speed of that electron is about 1 million meters per second. But what we're most interested in is kind of the forward progress velocity, and that's called the drift velocity. The very irregular path means that electron does not go very fast in that forward direction. That forward progress velocity or drift velocity for a typical wire is somewhere in the neighborhood of 1 millimeter per second. So it's not making progress forward very fast at all. If we ponder back to the light bulb and the stopwatch, none of the electrons have made it yet to the light bulb from the outlet because they just don't move that fast. So then why is the light bulb on? If none of the electrons have gotten to the light bulb, why is it lit? Why is it giving off light? Well, the thing we need to think about is where are these electrons coming from? They don't come from the outlet. They don't come from a battery. Those things are not really sources of electrons. Those things are sources of electric potential. In other words, your battery, your outlet, provides the push, the reason for the charges to flow. But those charges that are flowing are actually already in your wire. So then these atoms, and I'm going to steal my electron that I used a minute ago, these atoms have electrons, and when you establish that potential difference, those electrons that are already in the wire begin to move and flow and cause the light bulb to light. Prior to there being a potential difference or a voltage, those electrons are just moving around arbitrarily. If we were in class, we would have done this as a hands-on demonstration where I would have had one volunteer to be an electron, and we would have blindfolded that person. Two other volunteers, one to serve as high potential and one to serve as low potential, to guide the electron through the wire, and everybody else in class would have been one of those atoms, and we would have been sandwiched between two lab tables, and that electron would have to make it from one end to the other end, and that would be a time-consuming process because there's so much in the way. Similarly, back on our light bulb and stopwatch, it's just under 8 minutes, and none of the electrons have made it from the outlet to the filament of the light bulb because the electrons move so slowly because the atoms get in the way. So now let's consider a couple of analogies to really understand what's going on in an electric current. So we have a wide open field. Down at the bottom, That's a stick figure of you. And we are going to put a blindfold on you so you can't see. You're brightly colored so you show up on various different backgrounds. So there you are in the middle of this field. So imagine we took the whole class, we blindfolded everybody, we put them in the middle of an open field, and I yelled, "Go," and you started running as fast as you could. Well, if you picture that, that's what electrons are doing inside a wire when there is no battery, when there is no electric potential or potential difference. Those electrons just take off and they go and they move, and there are lots of them moving around in various different directions. And so they just move around. Now, this is a simplistic way of thinking about them. So a wire is not exactly like an electric field because a wire has atoms. So then to simulate those atoms, instead of a field, let's have a forest of trees. And now we're going to bring you and put you in the middle of this forest. Now imagine the whole class was blindfolded in the middle of the forest, and I yelled, "Go," and you started to sprint. Think about what would happen. You would run, bam, you would run into a tree, and you'd bounce off. And then you start running again, and bam, you'd run into a tree, and you'd bounce off. And you start running again, bam, you'd run into a tree. And that's exactly what happens to electrons inside a wire when there is no battery or electric potential difference. They are moving around arbitrarily at about 1,000,000 meters per second, and they just run into atoms. This still doesn't represent a circuit because we don't have a potential difference. So then to change this a little bit to represent a circuit, I'm going to take our forest, and you got to use your imagination a little bit here. I'm going to take our forest and I'm going to rotate it a little bit. So now it's not just a forest, but it is a hill. Here is our electron, our person, starting out somewhere on that hill. Now, there is an electric potential, and the analogy to that is just like the hill. So now when the electrons move, it isn't quite arbitrary anymore, but those electrons are given a direction down the hill. The electric potential gives the electrons a direction. They go toward low potential. So here's our person, and they start to go downhill. Wham, they run into a tree. They bounce off. Wham, they run into another tree. They bounce off. Boom, another tree. And they keep running into tree after tree after tree. And it takes them quite a while to get down to the bottom of the hill. An electron does not move very fast in a wire because there's so many atoms in the way. They just keep running into thing after thing after thing. Okay, and then they get to the bottom. They get to the low potential end of the battery. And then what happens? Well, they go through that chemical reaction. And that chemical reaction brings energy back to them and brings them back to the top of the hill, so to speak, to the high potential. And then our person, our electron, goes through the whole process again and again and again. But keep in mind that the electrons are the electrons that are in the battery, in all the parts of the wire, in anything that is in the circuit. So then I just want to really emphasize your battery. It is not correct to think of it as a source of charges because the charges are really coming from everything that is anywhere in your circuit. Once you have that battery, that potential difference, then they're motivated to move in a certain direction. It's not an organized motion. It is rather chaotic as billions of charges run into atoms and kind of find their way through. So a battery is not a source of charges, but it is a source of the reason for those charges to flow. And that reason is that it supplies that electric potential or potential difference. the high and the low. Simplistically, you can think of this as the push. It motivates the charges to move in a certain direction, but there's so much there in the way, there's so many atoms, that when you have an electric current, it is very slow. They don't make forward progress very long. In fact, if we ponder our light bulb, none of the electrons have made it yet from the outlet to the filament of that light bulb, by the sheer fact that the wire is too long. Based on the length of the wire and a simple V equals delta X over delta T term, those electrons will take about 30 minutes based on the length of that wire to be able to make it to the filament of the light bulb. So then back to our original question, why is the light even on if none of the electrons have gotten to the filament of the light bulb? Well, I want to emphasize again that a battery or an outlet is not a source of charges. The charge is already there in the wire, and so the light bulb goes on right away because the charges that are in the wire right next to the filament and in the filament are motivated to move. Now, once they move, and think back to the analogies, those moving charges run into atoms, and in running into the atoms, they transfer energy. That's what an electric current is all about. Motivate your charges to move, get them to run into things, and transfer that energy. And sometimes that energy transferred is expressed as heat energy, causing a wire to warm up. Sometimes that energy that is transferred is expressed as light energy in a light bulb. The light bulb gives off light. In a radio, that energy is transferred and sound is given off. And so it really depends on what the situation is as to what that energy becomes. But your battery, your outlet, motivate charges to move with a potential difference, and that energy transfer takes place. So an electric current is a slow thing. It's not about getting the charges to somewhere, but it's about motivating the charges everywhere in the circuit or the wires to move and run into things to be able to transfer their energy. So let's bring our light bulb to a close here. We're at just under 16 minutes. Still not a single electron has made it to the filament of the light bulb from that outlet. So what do we see when the electrons do make it to the outlet? Nothing different, because there are electrons already there that are colliding and producing light. If we waited for 30 minutes, which we're not going to do, it would look exactly the same as it does now. One more piece I want to throw into the picture, and that's Ohm's law. And this brings together our electric potential and our electric current. The more electric potential, when this becomes greater, that means that you're going to motivate more charges to move. You're going to have a higher electric current, and these are proportional to each other. We have a direct proportion or a linear relationship. Our proportionality constant we call resistance, which is basically conceptually the opposition to the flow of charges. And that's what you saw in terms of the atoms getting in the way, the trees getting in the way. And so then if we set up an equation, the ratio of V over I is equal to constant, remembering that V is your symbol for electric potential, I is your symbol for current. And so that constant is then equal to R, which is resistance. So we have the equation V over I is equal to R. Oftentimes we will multiply the I to the other side and write V equals I times R. And this is your Ohm's law equation that brings the different quantities we've been talking about together. Now, resistance, your unit of resistance is an ohm, which has a Greek letter omega. Now, let's consider this example. We have a fluorescent light bulb, 26 watts, 120 volts, operates on a current of 0.22 amps. So first of all, just identifying what these different things are. 26 watts, that's the power. And so basically that means a watt is a joule per second. 26 joules of energy are being converted into light energy every single second. 120 volts, that's the electric potential V. And 0.22 amps, an amp is current, so that is I. So then in part A, how many electrons are moving each second due to the current in the bulb? Well, that's going to be a picket fence. 0.22 amps, remember what an amp is. That's a coulomb per second. And so then once we think of that in coulombs per second, we can convert into electrons, because we know one electron has a charge of 1.6 times 10 to the negative 19th coulombs. So that's going to give us 1.25 times 10 to the 18th electrons. Each second, that's how many electrons are moving through the wire. That's 1,000,000 trillion electrons moving through the wires, moving through the light bulb every single second. Now in part B, we really want to think of this 0.22 amps and exactly what it means in terms of, is it a how far, is it a how fast, what that means. Well, we know, again, the units, that's coulombs per second, and coulombs per second relates to a number. So then when you're dealing with a current, it's a number of charges that are flowing. So then let's say we had a higher current. Let's suppose we had a current of 10 amps. That does not mean that the electrons are moving faster. That does not mean that the electrons are moving farther. What that means is that there are more electrons that are moving. So current is not a speed thing. It's not a how far, it's a how many. Larger currents, more charges are moving. Smaller currents, less charges are moving. But there's not really any significant difference in how fast those charges are moving. Now let's consider part C. Well, we can use our current equation, I equals delta Q over delta T, because what we want to find is how many coulombs of charge. So then my I value is 0.22 amps. My time period is 35 seconds. And we want to solve for delta Q. So then putting that over 1, if we solve down for delta Q, the charge value what we get there, 7.7 coulombs when we multiply 35 by 0.22. Part D. Calculate the resistance of the bulb. Knowing our voltage and knowing our current, we're able to use Ohm's law for this. V is equal to I times R. For V, we put 120 volts in. I is 0.22 amps. And then our resistance is the unknown. So then when we divide, we will get a resistance of 545.45 ohms. Now, there's one other thing I wanted to talk about that'll come up in the problem solving, and that's the idea of the quantity called a milliamp hour. Well, if we think about a milliamp hour, a milliamp, that's 1/1000th of an amp. An hour, well, in seconds, that's 3,600 seconds. So then in units, an amp is a coulomb per second. And essentially, I am multiplying this by a second because it's a milliamp times an hour, not a milliamp per hour. So coulomb times a second would just leave you with coulombs. And so a milliamp hour is actually a unit of charge. But it is commonly used with batteries. And the reason is because in a battery, you have a fixed amount of chemicals. And if you have a fixed amount of chemicals, that means you have a fixed amount of charge that can be pushed as a result of this chemical reaction. So let's say, for example, arbitrary number here, battery. A battery is rated 1,000 milliamp hours. Well, you can convert this into a number of coulombs, and you'll do that in the homework problems, but it would be a fixed number. If that's a fixed number, milliamps times hours, in terms of our equation, I equals delta Q over delta T. If I solve for delta Q, that would be I delta T. So that product of I delta T is equal to a constant, and that means that you have, at least for a battery, an inverse relationship here. So then on our 1,000 milliamp hour battery, well, I might be able to have 100 milliamps running. And if I have 100 milliamps running, that's going to last for 10 hours. Or maybe I have 1,000 milliamps running. Well, then my battery is only going to last for 1 hour. And so you can do some mental math because one goes up, the other goes down, but the product is going to remain constant with that value of milliamp hours. And so that is used oftentimes with different batteries. And you'll explore that more in the problem solving.